All right. So today we're doing problem 3028, ant on the boundary. Um, Today I was struggling to read the descriptions of some medium problems, right? Sometimes you wake up and you say, I'm going to do a Leetcode problem. And for whatever reason, in that particular day, that particular moment, you're just struggling to understand simple things, right? If you're opening up your computer and you're reading a whole problem description, it's not making sense, so then you go to the example and the description of the example and the solution doesn't make sense, it's probably not a good day to be doing Leetcode. I don't understand why there's any variance within our capacity to be intelligent, but that's something that I've experienced, and let me know if you've experienced it, right? Some days you can understand anything, your brain's quick, you're super intelligent, super sharp, and then other days you can't even figure out how to balance the binary search tree or whatever. Okay, so with that said, let's go ahead and get right into this. Should be pretty simple. All right, so an ant is on a boundary. It sometimes goes left and it sometimes goes right. Okay, you are given the array of non-zero integer nums. The ant starts reading nums, so the ant is going to be affected by whatever's in nums from the first element of its to its end. From the first element of it to its end. So it reads the array in order. Okay, at each step, it moves according to the value of the current element. Okay, so if nums of I is less than 0, it moves left. So it moves negative units. That makes sense, right? If I add in -5, I'm going to go left. All right. If nums I is greater than 0, it moves right by nums of I units. All right, well, makes sense too. The positive value, I go right? So if I get +5, I go right. If I get -5, I go left, -5. If I get +5, I go right, +5. If I get -5, I go left, 5, right? Return the number of times the ant returns to its boundary. So this kind of doesn't make sense, but maybe it's just because today I'm having trouble, articulating and comprehending simple concepts. But the boundary is the value that it starts at. Okay, so when you think boundary, you think of it having dimensionality, meaning like, okay, boundary is like from left to right. Like there's an area to it, right? There's a length to the boundary, I guess. But the boundary is literally just the position it starts at, okay? So whatever position it starts at, we're trying to figure out how many times does it end up on that position when it bounces left and right, okay? Now, some notes. So there's infinite space, so it's not like you can go too far right or too far left. We only check if the ant is on the boundary after it moves. So basically, if it passes the boundary, it doesn't count, right? But if you start somewhere and then you go forward and then you go back, but you go past it, that doesn't count as an additional... At least I imagine it doesn't count as an additional, like, a return to boundary. It doesn't count for an additional return to boundary, okay? So, basically all this problem means, right, is, okay, we have this, for example. Let's say we have this ant. It starts in its position, okay? It goes 2 units to the left. So this is its first boundary. We'll go boundary +1 is another position. Boundary +2 is another position. This would be boundary +3 as another position, boundary +4. And, likewise on the other side, you could do boundary -1, boundary -2, etc. So the ant initially starts on its boundary. The first step, it's going to go +2. So it's going to end up here, right? +2 over. Is it on its boundary? No. The next time it's going to go +3 over. So +1, +2, +3. So we need another boundary assessment here. And this would be boundary +5. And then on the next, is it on its boundary? No. And then it goes -5. So that's, -1, -2, -3, -4, -5 here, right? Because it was here. So it goes -1, -2, -3, -4, -5. Is it on its boundary? Yes. So we return 1. So it ended up back on its boundary 1 time. So it's, it's like moving around. It's bouncing around left and right, left and right. How many times does it touch its boundary? Okay. This one, 3, 2, -3, 4. Okay, so it starts here. It goes 3, 1, 2, 3. It goes 2, 1, 2. It goes -3, so it goes -1, -2, -3. So it goes back here. And then it goes -4. -1, -2, -3, -4. So see, it passed its boundary again, but just because it passes the boundary doesn't mean you get an additional point, right? It has to end up on the boundary. When it bounces around, it has to land on that boundary B, okay? So that's how this problem works. So we basically just start it, we simulate it. All we have to do is simulate it because, you know, our system is only less than 100. So we just simulate it, and then we say, okay, after each turn where we end up, do I end up on the boundary? That's it. Okay? So how can we do that? Well, notice if the boundary is a relative position, right? We don't know its value, but we only care about relative positions because if it's over here, right, we count how many times it kind of fluctuates between this position or over here, but it's relative to where the boundary is. So this B value can be anything. So what I mean by that is if I just set B to 0, watch what the magical thing that happens here. Right, because we're talking about relative positions. So the idea is, you know, the pluses and minuses that move us. Where we are initially doesn't really matter as long as we end up caring for the relative change that we do. Hopefully that makes a little bit of sense. So the idea is that this boundary value could be 0, which makes this much simpler because then I could just say, okay, well then this is just -2. You know, this is -2, this is -1. Our initial position is 0. Our boundary is 0, 2, 3, 4, 5, whatever. Right? So all I really need to do is add and subtract these things and figure out how many times do I land on 0, right? This works because I go 2 from the beginning, 3 from the beginning, and then I go -5 from the position, which gives me 0, right? That's why when I get this 0 value, right? Because this, you start at 0, then you end up at 2, you end up at 5, and here you end up at 0. So every time you end up at 0, that's at the boundary, right? So if we set our B value, our boundary value at 0, then we just do pluses and minuses and figure out how many times do I touch 0, okay? So we'll say our initial position is 0, right? Because we're at the boundary. All right. And then we'll look at each num and nums. And we're going to have our res solution equals 0. So this will be the number of times we touch the boundary. And then I'll just say, okay, our new position is whatever num plus equal nums, right? Because if nums is negative, it'll go left. So if nums is -5, it'll go -5 in our position, right? If nums is positive, and then we'll go positive nums in our position. And I'll just say, okay, do I end up at the boundary? Where's the boundary? The boundary is where I initially started. So maybe just to make this clearer, and it's not useful to do this, but if I say boundary equals 0 and our position equals boundary, and I can actually set this to anything, right? But is 0 simple? I say if my position is the boundary, well, then I just found another solution. And just like that, we solved this problem, I believe. I actually haven't submitted anything, so maybe there's some stipulation, but this seems pretty clear cut that that's the answer here. All right, cool. So what is the run and space time of this solution? Okay, so let's say n is the length of nums, right? For time, well, we create these 3 variables. It's constant time, and then we just run through all nums and do constant operations, right? We do a constant operation to add, we do a constant operation to compare, constant operation to append to res. So we look at n numbers, and we do constant things. So we do n constant things, so that's big O of n. And then for space, well, I just create these 3 variables, and then I update them accordingly, right? So independent of the size of nums, I'm just creating these 3 variables and updating them accordingly, so that's O of 1. All right, guys, hope you have a beautiful rest of your day. Bye-bye.